So in this video, I'll discuss the process of determining a net ionic equation. I'll also go through how to predict the product for a certain type of reaction that will help you with determining the net ionic equation. So that chemical reaction that I'm referring to is known as an exchange or a metathesis, or you could even hear double exchange or double replacement or even double displacement reaction. So all of those terms, even though they sound different, they mean the same thing. Essentially, with a metathesis reaction, you're starting with two compounds. It can be two ionic compounds or an acid and a base, but you're starting with two compounds. They basically swap partners and you end up with two new compounds. The general guideline or general formula for that is AX plus BY reacting to form AY plus BX. And so you had an example shown, silver nitrate reacting with potassium chloride. And so basically what happens is that the positive in the first compound, which is your silver, now pairs with the negative of the second compound, which is your chloride, to give a new compound, silver chloride, and then the opposite for the second compound. The negative and the positive come together, but you always write your positive ion first and then your negative ion. So we end up with potassium nitrate. So in order to determine how or what products are formed, you want to look at what you are starting with. So if you notice, you have silver nitrate and it's showing AQ. That means aqueous, so it means that your silver nitrate is dissolved in water. Then you have KCl, potassium chloride, same thing, aqueous. That means that it is dissolved in water. So you may have already heard about electrolytes. Electrolytes are simply compounds that, when placed or dissolved in water, they dissociate or break apart into the ions that make up that compound. So in the case of silver nitrate, because it's aqueous, we can show the ions that would be present, your silver ion and your nitrate ion. Now, we're not concerned about the physical state or the number of ions, just the identity of those ions. The same thing with the potassium chloride. You have your potassium ion and your chloride ion. So to predict the product, again, this positive now pairs with this negative. This positive now pairs with this negative. And so when these compounds pair, ionic compounds are formed when oppositely charged ions combine in the lowest ratio. So silver has a +1 charge, chloride has a -1 charge, so you only need one of each, which is where that AgCl formula came from. Potassium has a +1, nitrate is a polyatomic ion that has a -1 charge, so again, you only need one of each. So you may have already seen a solubility table, and I'll show an example. So a solubility table allows us to look at ionic compounds and determine whether or not they're going to be soluble or insoluble in water. So in that example shown, we have the silver chloride. So we have to look for that ion, silver, which is here. And with that ion, so that's our anion, we have to look at the fact that chlorides are generally soluble. But you always want to look at your exceptions. So you want to look over here. These exceptions mean that whatever cation is paired with that chloride, if it's one of those three, it's going to be insoluble. So your exceptions mean the opposite. So because chlorides are generally soluble, the exceptions are going to be insoluble. In this case, we have silver chloride. So it's going to be insoluble. We also have potassium nitrate. So if we look at our nitrates, the very top row, they're soluble and there are no exceptions, meaning that all nitrate compounds are going to be soluble. So that allows us to determine our physical state. So that is how we have solid for silver chloride because it was insoluble because of that silver exception, and aqueous for potassium nitrate because they were all soluble. So when we look at the formula for our reactants and our products, even with the physical states, when we show those formulas, that's what's called a molecular equation. Now, some call it a complete equation or just a chemical equation, but that shows the chemical formula as well as the physical state for all reactants and products that are present in that reaction. So silver nitrate in the aqueous form combining with silver chloride in the aqueous form will react to form solid silver chloride and aqueous potassium nitrate. So one thing to keep in mind again, because we have ionic compounds present and they are dissolved in water, and again we know that because of the aqueous, electrolytes tell us that when ionic compounds dissolve in water, they dissociate or ionize or basically break apart into their individual ions. So even though we have AgNO3 aqueous shown, what really happens when these substances and solutions are combined, what really happens is that we end up with aqueous silver cation, so that ionic form. We also end up with aqueous nitrate, which is our polyatomic ion. We also end up with aqueous potassium ion, and we end up with aqueous chloride ion. And then for the product side, we had AgCl. It was a solid, meaning that it does not break apart. It is still a solid. So we would not show that as an ion. But then we have the potassium nitrate that was aqueous, so it would also be shown as an ion. So again, whenever you have ionic compounds that are soluble, so in other words, they're in aqueous form, they're going to actually exist as the cation and anions that make up that compound. So when we show this, this is what is referred to as an ionic equation. Your ionic equation shows all of those electrolytes that have now dissociated to form the individual ions. So again, strong electrolytes are ionic compounds that are soluble, strong acids, strong bases. Those will completely break apart to only form ions. So even though we may write it as AgNO3, because it's an ionic compound that is soluble in water, it is a strong electrolyte, meaning that as soon as it's dissolved in water, it is no longer AgNO3, but instead it's Ag plus and NO3 minus. And so in the ionic form, you're just seeing all electrolytes. So you're seeing all ions of the aqueous solutions that are present. So when we look at this, if you notice, in this form, we have nitrate on our reactant side and nitrate on our product side. The exact same ion in the same physical state. The same thing with the potassium ion. K plus on both sides of the reaction. And again, we know this is both sides of the reaction because we have our reaction arrow. To the left are our reactants, to the right are our products. So because we have identical ions on both sides of the reaction, these are known as spectator ions. Spectator ions mean that they are present, they're spectating, but they're not really participating in the overall reaction. So an example that I like to give is if you've ever been to a basketball game or a football game, when you were there as a spectator. You were looking at the players play basketball or play football, but you were not actively playing basketball or football. So you were there in somewhat of a supportive role. You were there to observe, but not actually participate in the game. The same thing with these ions. They are there to observe, but they're not really participating in the formation of this solid precipitate. And I did not mention before, precipitate, so that term is formed when a precipitation reaction takes place. A precipitation reaction occurs when you have two aqueous solutions that combine to form a solid. That solid is known as the precipitate. That type of reaction is known as a precipitation reaction. So when I mentioned earlier about the metathesis reaction, the double exchange, double displacement, whichever term you use, precipitation is a form of that specific type of reaction. We have those two compounds that combine to form two new compounds, but when those two aqueous solutions combine in a solidus form, it's known as a precipitation reaction. So again, we had the silver nitrate with potassium chloride, both were aqueous, but because we ended up producing this solid silver chloride, this was a precipitation reaction. So spectators, they do not participate in the formation of this precipitate. Because if you notice, what we end up with is our silver ion, chloride ion, and our silver chloride. Spectator ions, similar to what you see in math. When you have the same thing on both sides of the equation, just imagine them canceling each other out. So these would cancel out. So they're not actively participating in this reaction. They're not basically producing this precipitate that was formed. So your ionic equation shows all ions. When we identify identical ions on both sides of the equation, those are known as spectator ions. Spectator ions, just like in math, because they are identical on both sides of the equation, they cancel out. Once we cancel out those spectator ions, what we're left with is known as the net ionic equation. These are the ions that are responsible for the formation of this precipitate. So a net ionic equation simply ignores those spectator ions and shows what is responsible for producing the solid in this reaction. And so that is the process of identifying a net ionic equation. To do this, you want to start with a molecular equation, which shows the complete chemical formula of all reactants and products. Any that are ionic or strong acids or strong bases that are in the aqueous form, they would then be shown as ions, which gives us our ionic equation. From there, we can identify when we have identical ions on both sides of the equation. Those are our spectator ions. We cancel them out to leave us with the net ionic equation. So that's the process, but I will do a couple of examples with you just to make sure that you understand how to apply the concept. So the first asks that you predict the product formed when aqueous solutions of FeCl2 and K2SO4 are mixed. So FeCl2 and K2SO4. So when these come together, we have two compounds. So that means that we're going to be looking at a double displacement or a double exchange reaction. I'm going to rewrite this to make it a little smaller. So FeCl2 plus K2SO4. So to predict our products, we have to identify what type of ions are present in these compounds. So FeCl2, so if you know how to name ionic compounds that involve transition metals, so iron is a transition metal that can have multiple charges, we have to look at this formula to determine what charge of iron is present. Because we have chloride, chloride is a halogen. All of your halogens, when they form ions, they form a -1 charge. So they generally will form a -1 charge. So because I have two of them, what that tells me is that my total negativity is -2. So my total positivity needs to be +2. So that means that this iron is in a +2 form. But if you could look at the FeCl2 compound and name it, you would know the name is iron 2 chloride. That iron 2 tells me the charge on my iron. So the type of ion present in that compound is iron with a +2 charge and chloride with a -1. I'm not concerned about the fact that there are two of the chloride ions. I'm only concerned about the identity and the type of ion present. Same thing with potassium sulfate, so K2SO4. Potassium is an alkali metal, group 1A. It's going to have a +1 charge. Sulfate is a polyatomic ion with a -2 charge. So sulfate has a -2. Each potassium has a +1, which is why you need two of them. But again, the number does not initially matter. So from there, we're basically swapping partners. This positive will now pair with this negative. This positive will now pair with this negative. Once you know the positive and the negative that pair, you can determine what the chemical formulas are. So remember, in the formula for an ionic compound, you always show your cation, which is your positive charge, first, followed by the anion, which is the negative charge. So it doesn't matter which one you show first, as long as you show them both on the product side. So if we start with the iron, iron has a +2, sulfate has a -2. When ions combine, they're combining in the simplest or the smallest ratio. So that +2 and the -2. They have to combine in a way that the charges cancel out. So because I have a +2 and a -2, I only need one of each. Because for every +2, it's going to cancel out that -2. So that formula would simply be FeSO4. And so I got that by combining these two ions. plus 2 and minus 2. Whenever they have the same value, you only need one of each. So if I had a plus 2 and a minus 1, or plus 2 and a minus 3, then I'm going to have subscripts present. But because I have the same value, plus 2, minus 2, I only need one of each. Same thing with the potassium ion and the chloride. I have a plus 1 and a minus 1. Again, I have to show the positive first, so I would write it as KCl. So these are my two products for this reaction. Now I can take it a step further, because if you were asked to do the molecular formula, we would need the physical states. So if we go back to our solubility table, we have iron 2 chloride. Chlorides are generally soluble, but iron is not an exception, so it's still soluble. We also had potassium sulfate. Sulfates are generally soluble. The exceptions are strontium, barium, mercury, and lead. So again, that is not an exception. So that means that it is also soluble. So both of our reactants are aqueous. Same thing with the products. Sulfate. Again, we have iron sulfate that we're looking at now. Iron is not one of the exceptions, so it is still soluble. And then potassium chloride. Potassium is not one of the exceptions, so that means that it is also still soluble. So what that means is that all of these are in the aqueous form. So it's still a double displacement, or an exchange, or metathesis, whatever term you want to use. It's still that type of reaction. However, this is not a precipitation reaction because we do not form a solid. So what would happen if we were actually to go through and look at the net ionic equation? We would have to first identify our complete ionic equation. Everything would be in the ionic form. So the problem didn't ask us to do that. I'm just showing you just to make sure you're understanding. So because everything is aqueous, this would be in the aqueous form. Now I do need to know the number of each ion. Every time this breaks down, the FeCl2, I'm going to end up with one iron ion and two chloride ions. They're still aqueous. Same thing with the potassium. Every time this compound breaks down, I'm going to end up with two of the potassium cations and one of the sulfate. Product side. My products are both aqueous. So again, I'm going to end up with ions. Iron 2 sulfate breaks down. Potassium chloride also breaks down. Now, one thing that I failed to do, I didn't show that there would actually be a 2 here to balance that equation. So I'm going to end up with 2 here and 2 there. So now if we identify spectator ions, we have Fe2 plus, Fe2 plus, 2Cl minus, 2Cl minus, 2K plus, 2K plus, 1 SO42 minus, 1 SO42 minus. So we would not have a net ionic equation for this reaction. So again, with the ionic equation, it allows us to see all ionic compounds or strong acids, strong bases that are aqueous, shown as ions. From there, we cancel out those that are on both sides, which are our spectator ions. What's left gives us a net ionic equation. In this case, everything canceled out, so we do not have a net ionic equation. So in the next example, now you're asked to write the net ionic equation for the precipitation reaction that occurs when aqueous solutions of calcium chloride and sodium carbonate are mixed. So this problem gave you some clues. It told you were dealing with a precipitation reaction. It told you that these reactants that are combining are both aqueous. So it lets you get started. You were also asked to write the net ionic equation. So in order for us to do the net ionic equation, we have to identify the molecular equation, the ionic equation, identify spectator ions, and then we'll know what our net ionic equation is. So if we get started, we can show what our molecular equation is for this reaction. So when we combine the calcium chloride, again, the problem already told us it was aqueous. We can confirm that on the solubility table, but I'll just go ahead and show it here. With the sodium carbonate, we first have to identify what ions are present. Because these are both ionic compounds, we know that they're soluble, so we know that ions would exist. Again, initially, I'm only concerned about the type of ions. So I have the calcium ion. Calcium is an alkaline earth metal, group 2A. So it's going to have a +2. I have chloride. There are 2 present. They're halogens. Each one has a -1. I have sodium, which is an alkali metal, group 1A. So it has a +1. There are 2, so each one has a +1. And then I have carbonate. Carbonate is a polyatomic ion with a -2. So to predict the product, this positive will now pair with this negative. This positive will now pair with this negative. So when we look at this, we end up with calcium, which has a +2, combining with carbonate, which has a -2. So we only need one of each. So we have CaCO3. We end up with sodium, which is a +1, combining with chloride, which is a -1. So we have NaCl. So if we go back to our solubility table, we can determine the physical states. So were they or were they not soluble in water? So calcium carbonate. Carbonates are towards the bottom. So this bottom section shows you things that are insoluble. So carbonates are generally insoluble, but we have to look at the exceptions because the exceptions are going to be soluble. The exceptions include ammonium, which is a polyatomic ion, and alkali metals. Alkali metals are group 1A metals. However, we have calcium, which is an alkaline earth metal, a group 2A. So it's not included in the exception, so that means that this is going to be insoluble. And then we have sodium chloride. Chlorides are up top. These are generally soluble. The exceptions are silver, mercury, and lead. Sodium is not an exception, so it is still soluble. So what that means is since our calcium carbonate is insoluble, it's going to be a solid. Sodium chloride is soluble, so it's going to be aqueous. So from there, we can actually balance our equation. So when we're balancing equations, the molecular equation is what we use to balance the equation. So when I balance an equation, what I generally do is write the atoms that are present, or in this case, I can show it as ions. That's a trick when dealing with double exchange reactions, but you have to be careful because sometimes this breaks down. So you can show it as that, but I like to just go ahead and take the extra step and do it the right way and just show the individual atoms. On the reactant side, I have 1 calcium, 2 chlorine. So I'm looking at CaCl2. That's the only place where I have calcium and chlorine. For every one of these, I have Ca. I have to look at the subscript. I don't see anything, so there's an invisible 1. And I have 2 chlorine as a subscript. The subscript is always written to the right of the element that it refers to. Same thing with sodium carbonate. I have 2 sodium. I don't see anything for carbon, so that means 1. I have a 3 for oxygen. So 2, 1, 3. I need to do the same thing on the product side. So I have 1 calcium, 1 carbon, 3 oxygen. So nothing there, so invisible 1s, and then my 3. Same thing with sodium and chlorine, invisible 1s, because I don't see anything. So everything is balanced except for sodium and chlorine. So to balance an equation, you have to add a coefficient. So I can add a 2 here. A coefficient tells me how many of this individual compound would be needed. Because only sodium and chlorine are in that compound, it's going to only change the number of those 2 atoms present. So now I have a balanced equation. So from there, this is our molecular equation. So I'm going to rewrite this on a clean page. So CaCl2, which was aqueous. We had Na2CO3, which was aqueous, reacting to form CaCO3, which was solid, and 2NaCl, which are both aqueous. So that's our molecular equation. I just put an M by it. From there, we can determine our ionic equation. Because remember, when we have ionic compounds that are aqueous, they're going to actually exist as an ion. So even though we may add calcium chloride, once we dissolve it in water, it breaks apart to give us those individual ions. So we end up with the calcium ion. So every time this compound breaks apart, it forms one calcium cation and two of the chloride anions. Every time sodium carbonate is dissolved in water, so again it's ionic and it's aqueous, so every time it dissolves, it's going to form two of the sodium cations and one of the carbonate polyatomic ions. Product side, calcium carbonate is not soluble in water, so it will not break apart to form any ions. But sodium chloride will. Both of them will. So when both of them break down, I'm going to end up with two of the sodium cations and two of the chloride anions. So that's our ionic equation. From there, we can identify our spectator ions. So what ions do we have on both reactant and product side? I have two Cl- on both sides. I have two Na+ ions on both sides. So those are our spectator ions. So we can just imagine canceling them out. We won't include them anymore. What we're left with from there would be our net ionic equation. So the net ionic equation, I'm just going to show it as Ni, net ionic. Our net ionic equation, what do we have left? We have the calcium cation, which was aqueous. We have the carbonate ion, which was aqueous. That's all that we have on our reactant side. Product side, we have calcium carbonate, which is still a solid. And that gives you your net ionic equation. So again, with the net ionic equation, it's simply showing what ions make up this precipitate. So I hope that this helps, but if you have any other questions, please let me know. Thank you.